Yes, there is a standard formula for calculating line losses in amps per kVA for a dry-type transformer. The formula is line losses in amps per kVA equals the impedance percentage divided by 100, multiplied by the rated current. To apply this formula, the rated kVA of the transformer and its impedance percentage need to be known. Also, the rated current on the primary side is also needed, which can be calculated as follows. Rated current equals kVA divided by the quantity of voltage times the square root of 3. To illustrate, consider a 75 kVA transformer with a 480 volts primary and an impedance of 5 to 6%. Firstly, calculate the rated current. Rated current equals 75 kVA divided by the quantity of 480 volts times the square root of 3, which is approximately 91.29 amps. Secondly, calculate the line losses for both 5% and 6% impedance. For 5% impedance, line losses equal 5 divided by 100 multiplied by 91.29 amps, which is approximately 4.56 amps per kVA. For 6% impedance, line losses equal 6 divided by 100 multiplied by 91.29 amps, which is approximately 5.48 amps per kVA. Therefore, for the given dry-type transformer, the line losses are approximately 4.56 to 5.48 amps per kVA for an impedance range of 5 to 6%. It is important to remember that this formula yields an approximation of the line losses. Actual losses may vary slightly based on the specific transformer design and its operating conditions. The impedance percentage is a crucial parameter in determining these losses. Transformers with higher impedance percentages will generally exhibit higher line losses. The nameplate of the transformer should contain information such as the KVA rating, primary and secondary voltages, and impedance percentage. Line losses in a transformer are primarily due to two factors, namely, copper losses or I2R losses and coal losses or iron losses. Copper losses occur in the windings of the transformer due to the resistance of the copper wire and the current flowing through it. These losses are proportional to the square of the current. Coal losses occur in the core of the transformer due to the alternating magnetic field. These losses are further divided into hysteresis losses and eddy current losses. Hysteresis losses are caused by the energy required to continually realign the magnetic domains in the core material during each magnetization cycle. Eddy current losses are caused by circulating currents induced in the core material by the changing magnetic field. The formula provided focuses on an approximation based on impedance, encompassing both copper and coal losses implicitly within that impedance value. However, to calculate the actual losses more accurately, one would need to perform load tests and open circuit tests to determine the individual contributions of copper and coal losses. When selecting a transformer for a particular application, it's important to consider the expected load profile. Transformers are most efficient when operating near their rated capacity. Operating a transformer at significantly lower loads can decrease efficiency as coal losses become a more significant portion of the total losses. In addition, ambient temperature and ventilation play a role in transformer performance. Higher temperatures can increase the resistance of the windings, leading to increased copper losses. Proper ventilation is essential to dissipate heat and maintain the transformer within its operating temperature limits. Furthermore, harmonic currents in the load can also increase transformer losses. Harmonic currents cause additional heating in the windings and core, reducing efficiency and potentially shortening the lifespan of the transformer. K-rated transformers are designed to withstand the effects of harmonic currents. Regularly inspect the transformer for signs of overheating, such as discoloration or bulging of the enclosure. Also, check for unusual noises or vibrations, which may indicate loose connections or other mechanical issues. Performing regular maintenance, including cleaning and tightening connections, can help ensure optimal performance and extend the lifespan of the transformer. Remember that the NEC or National Electrical Code provides guidelines for the installation and protection of transformers. It covers aspects such as overcurrent protection, grounding, and clearances. Always comply with the applicable codes and standards when installing and maintaining transformers. The efficiency of a transformer is defined as the ratio of output power to input power. It's usually expressed as a percentage. High-efficiency transformers minimize energy waste and reduce operating costs. When comparing different transformer models, pay attention to their efficiency ratings. Also consider future load growth. Selecting a transformer that is adequately sized for current and future needs will ensure reliable operation and prevent overloading. Overloading a transformer can lead to overheating, reduced lifespan, and even failure. Finally, consult with a qualified electrical engineer or technician for specific applications or complex calculations. They can provide valuable insights and ensure that the transformer is properly selected and installed. Understanding transformer line losses and efficiency is crucial for optimizing electrical system performance and minimizing energy consumption. By applying the formula and considering other relevant factors, informed decisions about transformer selection, operation, and maintenance can be made. The formula gives an approximate loss, but the actual losses can vary based on the specific transformer's characteristics and operating conditions. Here are some factors that can cause the actual losses to differ from the calculated approximation. Firstly, manufacturing tolerances. The impedance of a transformer can vary slightly from its nameplate value due to manufacturing tolerances. This variation affects the calculated line losses. Secondly, temperature. The resistance of the transformer windings increases with temperature. Higher temperatures lead to increased copper losses, which in turn affects the total line losses. Thirdly, load level. The line losses vary with the load level. The impedance-based formula provides a reasonable approximation near the rated load, but the accuracy decreases at significantly lower or higher load levels. Fourthly, harmonic content. The presence of harmonic currents in the load can increase transformer losses, especially eddy current losses in the core. Fifthly, transformer design. Different transformer designs have varying core and winding configurations which affect the distribution of losses. Sixthly, core material. The properties of the core material, such as its permeability and hysteresis characteristics, affect the core losses. Seventhly, winding insulation. The type and quality of winding insulation affects the dielectric losses and the operating temperature of the transformer. Eighthly, cooling method. The effectiveness of the transformer's cooling system affects its operating temperature and therefore the winding resistance and copper losses. Ninthly, aging. As a transformer ages, its insulation degrades and its core material may experience changes in magnetic properties. These changes affect the losses. Tenthly, applied voltage and frequency. Variations in the applied voltage and frequency can affect both the core and copper losses. It is good practice to measure the actual line losses under typical operating conditions to get a more accurate assessment. This can be done using power quality analyzers and data logging equipment. By using such tools, one can assess the actual losses and compare them to the calculated approximations and adjust the transformer's loading or operating parameters as needed to optimize its performance and efficiency. The approximation of line loss using impedance is a good starting point, but practical considerations are always important for real-world applications. It is also good to check with the manufacturer's specifications for detailed information on the transformer's performance characteristics. Transformer efficiency is a critical parameter in electrical power systems. It represents the ratio of output power to input power and is typically expressed as a percentage. A higher efficiency rating indicates lower losses and more effective power delivery. Here are some factors affecting transformer efficiency. Firstly, load level. Transformers generally operate most efficiently near their rated load. As the load decreases, the core losses become a larger percentage of the total losses, reducing efficiency. Secondly, transformer size. Larger transformers tend to have higher efficiencies than smaller transformers because the core-to-volume ratio is reduced. Thirdly, design and materials. The design of the transformer, including the core material, winding configuration, and insulation, significantly affects its efficiency. High-quality materials and optimized designs minimize losses. Fourthly, operating voltage. The operating voltage affects the core losses. Transformers designed for higher voltages tend to have lower core losses. Fifthly, frequency. The operating frequency affects both core and winding losses. Transformers designed for specific frequencies operate more efficiently at those frequencies. Sixthly, ambient temperature. Higher ambient temperatures increase winding resistance, leading to increased copper losses and reduced efficiency. Seventhly, harmonic distortion. Harmonic currents in the load increase transformer losses, especially in the core, reducing efficiency. Eighthly, cooling method. Effective cooling systems maintain lower operating temperatures, improving efficiency by reducing winding resistance. Ninthly, aging. As transformers age, their efficiency can degrade due to insulation breakdown, core material changes, and other factors. Tenthly, impedance. Lower impedance transformers can have lower voltage drops but potentially higher circulating currents, affecting efficiency. There are different types of transformer losses that affect overall efficiency. Copper losses, which are also known as I2R losses, occur in the primary and secondary windings due to the resistance of the copper conductors. These losses are proportional to the square of the current. Core losses, which are also known as iron losses, occur in the transformer core due to the alternating magnetic field. They consist of hysteresis losses and eddy current losses. Hysteresis losses are caused by the energy required to repeatedly magnetize and demagnetize the core material. Eddy current losses are caused by circulating currents induced in the core material by the changing magnetic field. Dielectric losses occur in the insulation materials of the transformer. These losses are generally small compared to copper and core losses but can become significant at high voltages. Stray losses are losses that are not easily categorized, such as losses in the tank, clamps, and other structural components. These losses are typically small but can contribute to the overall losses. The formula for transformer efficiency is efficiency equals output power divided by input power, which is then usually multiplied by 100% to express it as a percentage. The input power is equal to the output power plus the losses, meaning efficiency equals output power divided by the quantity of output power plus total losses, multiplied by 100%. Minimizing transformer losses improves efficiency and reduces operating costs. Here are some strategies for minimizing losses. Firstly, use high-efficiency transformers. Select transformers with high efficiency ratings, especially for applications with continuous or high load factors. Secondly, optimize loading. Operate transformers near their rated load to maximize efficiency. Avoid oversizing transformers, which can lead to reduced efficiency at lower loads. Thirdly, reduce harmonic distortion. Use harmonic filters or K-rated transformers to mitigate the effects of harmonic currents on transformer losses. Fourthly, improve cooling. Ensure adequate ventilation and cooling to maintain lower operating temperatures and reduce winding resistance. Fifthly, use amorphous core transformers. Amorphous core transformers have lower core losses compared to traditional silicon steel core transformers, resulting in higher efficiency. Sixthly, regular maintenance. Implement a regular maintenance program to inspect and maintain transformers. This includes cleaning, tightening connections, and replacing worn components. Seventhly, power factor correction. Improve the power factor of the load to reduce current and minimize copper losses. Eighthly, voltage regulation. Maintain proper voltage levels to minimize voltage drops and improve efficiency. Ninthly, load balancing. Balance the load across the three phases to reduce neutral currents and minimize losses in three-phase transformers. Tenthly, energy audits. Conduct regular energy audits to identify opportunities for improving transformer efficiency and reducing energy consumption. It is also important to understand transformer nameplate data. The transformer nameplate provides critical information about its specifications and operating characteristics. Key parameters include KVA rating, which indicates the apparent power that the transformer can deliver without exceeding its temperature limits. Voltage ratings specify the primary and secondary voltages for which the transformer is designed. Current ratings specify the primary and secondary currents at the rated KVA and voltage. Frequency ratings specifies the frequency at which the transformer is designed to operate. Impedance specifies the transformer's impedance as a percentage, which is important for calculating fault currents and voltage regulation. Temperature rise specifies the maximum temperature rise of the windings above the ambient temperature at rated load. Insulation class specifies the thermal class of the insulation materials used in the transformer. Vector group specifies the phase relationship between the primary and secondary voltages in three-phase transformers. Efficiency specifies the transformer's efficiency at rated load. Standards compliance indicates the standards to which the transformer complies, such as IEE or IEC standards. Understanding and correctly interpreting the nameplate data ensures that the transformer is operated within its design limits, maximizing its performance and lifespan. Consider a scenario where the transformer is operating at a load significantly below its rated capacity. In this case, the core losses become a larger percentage of the total losses, reducing overall efficiency. To address this issue, one option is to replace the transformer with a smaller unit that is better matched to the actual load. Another option is to implement a transformer tap changer to adjust the voltage and improve efficiency at lower loads. Regular monitoring of transformer parameters such as voltage, current, temperature, and power factor is essential for ensuring optimal performance and identifying potential issues before they lead to failures. Modern transformers often come equipped with sensors and monitoring systems that provide real-time data on these parameters, enabling proactive maintenance and preventing costly downtime. Remember to always comply with relevant electrical codes and standards when installing, operating, and maintaining transformers. These codes provide guidelines for safety, grounding, overcurrent protection, and other critical aspects of transformer installations. Properly sized overcurrent protection devices such as fuses or circuit breakers are essential for protecting transformers from overload and short-circuit conditions. The overcurrent protection should be coordinated with the transformer's thermal overload capacity to prevent nuisance tripping while still providing adequate protection. Furthermore, proper grounding is crucial for ensuring electrical safety and preventing equipment damage in the event of a fault. The grounding system should be designed and installed in accordance with applicable codes and standards. To summarize, understanding transformer line losses and efficiency is crucial for optimizing electrical system performance, reducing energy consumption, and ensuring reliable operation. By considering the factors discussed and implementing appropriate strategies, one can maximize the efficiency and lifespan of transformers, contributing to a more sustainable and cost-effective electrical system. Always consult with qualified professionals for specific applications and complex calculations.